This is our third video dedicated to Bessey shuffle diagrams. Quick review. A shuffle S is said to be a Bessey shuffle if and only if S preserves or inverts Bessey sequences. Recall, the Bessey sequences of order 8 are 1, 0, 0, 1, 0, 1, 1, 0, and 0, 1, 1, 0, 1, 0, 0, 1. Also recall that the two sets of position values of importance to us are the following. The set A consisting of position values 1, 4, 6, 7, and A complement consisting of the position values 2, 3, 5, 8. Also recall, if position values stay within their respective sets after performing the shuffle, then we denote that outcome as follows, as indicated here. If inversion occurs, this is how we represent that outcome. And to quickly remind you, inversion occurs when the cards in positions 1, 4, 6, 7 get moved to positions 2, 3, 5, 8. So it's as if the position values in these two sets get switched, and we call that an inversion. And to aid us in distinguishing between the elements in A and A complement, the digits here have been color-coded. Also remember that the two Bessey sequences of order 8 are 1, 0, 0, 1, 0, 1, 1, 0, in which the 1s are in positions 1, 4, 6, 7, and the 0s are in positions 2, 3, 5, 8. For the inversion of this Bessey sequence, namely what's written here, the 0s and 1s switch places. Consequently, there are only two possibilities for Bessey sequences of order 8, as listed here. So moving on to our next shuffle in this series, let's take a look at shuffle number 9, which is the top left shuffle on the diagram to the left. And we call this shuffle an Even-UpJog. So as always, we'll begin with an ordered packet, 1 through 8, and then we'll perform our shuffle, record the outcome of that shuffle, and then describe the permutation involved, first in Cauchy's two-line notation, and then we'll rewrite that in cycle notation. Okay, so what is an upjog? Or in particular, what is an even-upjog? Well, this is where you push forward or jog forward the even position cards. That's all you're doing. And then you strip those out. Now we have a left and right hand pile. And so for this first upjog shuffle, we will be stacking the left pile on top of the right, as indicated right there. Okay? So let's take a look at the new ordering of the packet. Okay? So we get 2, 4, 6, 8, 1, 3, 5, 7. That's kind of interesting. So let's take a look at what I've written up formally. So here is the two-line notation in which I've indicated that we now have the ordering 2, 4, 6, 8, 1, 3, 5, 7. Now we can rewrite this in cycle notation as follows. 1 goes to 2, so I have an arrow from 1 to 2. 2 goes to 4. 4, where's 4? 4 goes to 8. 8 goes to 7. And 7 goes to 5. And finally, 5 goes to 1. So it wraps back around. So we have a very large cycle, larger than the ones that we've seen in the past. This is a 6 cycle. Now for the remaining values, what happens? Well, we have 3, which goes to 6, and 6 goes to 3, so that cycles around. So we're looking at a 2 cycle, or in other words, a transposition. Now if we color code the cycle notation of our permutation, we obtain the following. So remember, 1, 4, 6, 7 have been color coded black, 2, 3, 5, 8 have been color coded red. So we have black 1 being sent to red 2, which is sent to black 4, which is sent to red 8, which is sent to black 7, which is sent to red 5, and that wraps around and gets sent to black 1. Over here for the transposition, we have the red 3 being sent to the black 6, which gets sent back to the red 3. So as our color coding makes clear, each value gets sent to a value of the opposite color. And when that happens, inversion occurs. So what this means then is all of the cards in positions 1, 4, 6, 7 get moved somewhere to positions 2, 3, 5, 8. So that's what we mean by an inversion. Now in terms of Bessey sequences, using the digits 0 and 1, if we start with this particular Bessey sequence and perform this shuffle, we should expect the inversion of this sequence to occur. So why don't we just quickly demonstrate that. So I'll go ahead and do an evens. Even positions are being moved forward, even position cards, strip those out, and then left on right. So it should now be the case that we're looking at 0, 1, 1, 0, 1, 0, 0, 1, and we are. So our original Bessey sequence was inverted. Also, I should point out that we're looking at a 6 cycle, and I believe that's the longest cycle length that we've seen thus far. So in particular, what this will mean is it will take 6 applications of this particular shuffle to reset the packet back to its original order. So 6 of those are needed. Now it is true that during those 6 shuffles, 3 and 6 will be bouncing back and forth between each other. But by the time you perform 6 shuffles, 3 will be sent back to 3, and 6 will be sent back to 6. So it truly will return the packet to its original order. Okay, well let's go ahead and take a look at the Bessey shuffle diagram. Top left here. Now we've seen one similar to this. In fact, this is the inverse of 3. So in our very first video in this series, we saw this very graph except for the arrows being reversed. So if you take a look at shuffle 3, it'll be exactly this diagram here, but the arrows will be going in the opposite direction, which of course means that if we perform those 2 shuffles in succession, they undo each other. Okay, so why don't we just quickly step through this. 1 goes to 2, so down here. 2 goes down here to 4. 4 goes up to 8, right there. 8 goes to 7. 7 goes to 5 down here, and then 5 goes all the way back up to 1. So that completes that cycle. So that is a cycle of length 6, and it's also an orbit. So the numbers 1, 2, 4, 5, 7, and 8 are all in the same orbit. They just get moved around among themselves. And then because we have a single transposition right here, 3 and 6, we'll get a double arrow between values 3 and 6. So for each time you perform that shuffle, 3 gets sent to 6 and 6 gets sent to 3. So they just switch places. And of course, if they switch places 6 times, they're back in their original locations. And up here, we've noted the fact that inversion has indeed occurred.